Welcome. This class is STA2023 Introduction to Statistics, and I am Dr. Kim Milner. I'll be your instructor for this semester. Now, basically, I wanted to go over a few of the basics of the course. If you're taking this class online or if you are taking it face-to-face, both of you will be doing your homework and your quizzes for each chapter in something called My Open Math. That will be found in your Blackboard shell, and you'll be able to get information on that later. Your homework will have unlimited attempts at it, and the quizzes will be 4 attempts to each quiz. There will be 4 tests included, and this is also including the final exam, which we call Test 4. They are not comprehensive. Test 1 just covers chapters 1 and 2, 2 covers 3 and 4, 3 covers 6 and 7, and the final covers chapters 8 and 9. If you're taking these in my face-to-face classes, you'll be using green Scantrons, and the test will be multiple choice. If you're an online student, you'll be taking them online, and you will be basically having some multiple choice questions, some open answer questions. Now, if you're an online student and you feel the need to come in and take a paper test, then just send me a message and we'll see if we can work something out. How to be successful in this class? Well, basically, the way to be successful is not to get behind in your work. If you're face-to-face, you need to attend every class. If you're online, you need to set up a schedule and stay on track every week. You're going to be working weekly. You need to be working on statistics daily. There is a lot of vocabulary. Statistics is not your normal math class. You're going to be almost learning a new language. You want to practice the problems, work on the vocabulary, and pay attention to the test reviews that I've created. Now let's get started with the actual content of our course. First, let's look at some definitions. The most basic one is, what is statistics? Well, it's a science dealing with collection, analysis, interpretation, and presentation of data in order to make decisions. The in order to make decisions part is very important. There's no use doing the analysis of the data unless you have a decision to make. And this is what statistics gives you that so many other math courses don't give you. It gives you a practical, real-world application. It makes you a more valuable employee. So it applies to a lot of different careers. We're going to cover 2 basic types of statistics in this course. The first one is called descriptive statistics. Now, descriptive statistics, I think of those as pictures. They are methods of organizing and summarizing data. They use tables, graphs, and any other kind of summary measure. The numbers themselves, of statistical numbers, when we get all the raw data together, don't make a lot of sense unless we can organize it in a format that helps us make a decision. Descriptive statistics help us do that. The next type that we're talking about, or that you're responsible for, is inferential statistics. Now, this is methods that we use to take a sample of data and make decisions about a population. Most of the time, we are not able to get data on an entire population. Imagine, if you will, trying to take a survey of every man, woman, and child in the United States. It's very difficult to do. In fact, it's virtually impossible. So you can take a representative sample and see which way the sample goes on a certain question, and then you can infer, that's why it's called inferential statistics. You can infer that if the sample went that way, then probably the population would go that way too. Now let's talk about these 2 other very important terms that we'll be using for the entire semester. What is a population and what is a sample? Well, basically a population is an entire collection of persons or things or objects that you're studying. You're studying a certain characteristic of, most of the time, it's people. We take a survey, we find out what people think or what they do or what they own or what they buy, and that is the characteristic that we are studying about that population. Since we can't, quite frequently, we can't survey the entire population, we can get a representative sample. Now, the idea of sampling is to select a portion, which is really a subset, and to study that portion. We're only studying the sample to get more information about the population. The data that we pull are the result of sampling from a population. Now, hopefully you've been watching this and filling in your guided note pages as we go, because the guided note pages, which are in the book that I gave you, or either the ones that you're printing out from Blackboard, are the same. But these guided note pages are basically, this is your handbook, your workbook that's going to get you through this course. I've got an activity for you on page 2 of your guided notes of Chapter 1, and you should be there now. It says, explain whether each of the following is either a population or a sample. Now I want to do this with you because I want you to note certain key words. You want to circle these words. The first one says the number of pizzas ordered on Fridays during 2018 at all of the pizza parlors in Port St. Lucie. Now, is it a sample or is it the entire population? You're looking for certain words. All, each, every usually are used to denote the population. In this one, we see the word all of the pizza parlors in Port St. Lucie. So first one, Part A, is really population data. Let's look at Part B. The dollar values of auto insurance claims filed in 2019 for 100 randomly selected policies. Now there's your key words, randomly selected. As if you didn't know that there were more than 100 policies on claims filed in 2019. Obviously, this is not all of the claims that were filed in 2019 when there's only 100 of them, but the randomly selected tells us that this is sample data. Part C. The opening price of each of the 500 stocks in the S&P 500 Stock Index on January 1st, 2018. Look for the words. This says the price of each of the 500 stocks. In other words, every stock is represented. When we represent all of them, it's every one, each of the 500, that's population data. Now take D through H, stop your tape just a minute, take D through H, and see if you can complete those on your own, and then restart. Okay, you've had time to do this. Let's look at D, the total home attendance for each of the 30 major teams in Major League Baseball during the 2019 system. For each of the 30, every single team is represented. This is population data. The living areas of 25 houses listed for sale on March 7th, 2018 in Atlanta, Georgia. You should assume that there are more than 25 houses for sale in Atlanta, Georgia on any given date. This can't be all of them. This is sample data. The scores of all students in an algebra class. Did you find the word all? All will always tell you that this is population data. And the yield of corn per acre for 15 pieces of land in Iowa. Do you assume that there are only 15 pieces of land in Iowa, or do you think there are more than 15? Yes, probably more. So this is only a subset of the total. So this is sample data. Weekly earnings of all employees of a company. Well, even if there are only 3 employees of a company, we're choosing to survey all of them. That means we have dealt with the entire population. Okay, let's go on. We have lots of vocabulary in Chapter 1 especially. You might want to start thinking at this point about flashcards that have the definitions on one side and the word on the other side, so you can get really familiar with these terms. An element or a member would be of a sample or of a population. It's a specific person, an individual item. If we're surveying people, then it's the individual person. If we're surveying companies, then it's the individual company that we're collecting the information about. So we call each one of those an element or a member of our data set. A parameter is really a numerical characteristic. In other words, it's a number. And it's about the whole population. So when we talk about a parameter, it's really dealing with the population data. And we can use this to estimate. Now, if we consider all math classes to be the population, then the average number of points earned per student over all math classes would be a parameter because it was dealing with the data of the population. A statistic, on the other hand, is basically the same thing as parameter. It just deals with the sample data, though, instead of the population data. So if we randomly select 20 students and we look at the average number of points that each student earns over that sample, we call this a statistic, not a parameter. Those are two different terms. You're used to hearing the word statistic. Basically, you're used to looking at sample data. But parameter is the same thing, just dealing with the population. Now, a variable. That's a characteristic that we are studying, that's under study. And it can assume different values for different members of the population or samples. It can be numerical, it can be a number, it can be categorical, which is basically a category or a group that we put it into. And numerical variables will take on values with equal units, such as weight in pounds and time in hours. Categorical variables will place the person or thing into a category or into a basic slot that identifies them. It's almost like putting things in a box. This box is labeled Group A and this box is labeled Group B. Categories you think about as grouping. Now let's look at some examples of parameters and variables. Now let's say we want to know the average, which we call the mean, amount of money spent by first-year college students at Indian River State College on school supplies, and we're not including books in that. And we randomly survey 100 first-year students at IRSC. 3 of those students spent $150, $200, and $225. So what is the parameter that we're studying? Well, the parameter would be the average amount of money spent. Next, we look at the variable. We want to know the average amount of money spent by students at IRSC that don't include books, and here's our same information. We randomly survey 100 first-year students, and 3 of them spend the same amount. It's basically the same scenario. What's the variable? Well, that can be the amount of money spent, excluding books, by one first-year student. So we could say X is equal to the amount of money spent by one first-year student attending IRSC. Do you understand the difference? The parameter is the basic category that we put it into, and the variable is the actual money or the data. Take a look at some more basic terms, more flashcards for you. First is an observation or a measurement. Well, that is the value of a variable for an element. In other words, if we look at the amount spent and we say, well, this particular student spent $150, that's our observation for that student. That's the value of that variable. Data are the actual values of the variable. They can be numbers or words. They are the information that we collect when we do a survey. And a data set is a collection of observations on one or more variables. Now next we're going to take a look at types of variables. We split these basically into 2 different types, quantitative variables and qualitative variables. Now quantitative is like it sounds, it's quantities, it's numeric. And we have 2 different types of quantitative variables. They can be either discrete or they can be continuous. Qualitative variables, they don't split out at all. They're not really numbers as much as they're categories. So we can also call those categorical variables. Now a variable that's measured numerically is called quantitative. You can put out beside this one numbers because that's what you're going to remember it by. Quantities, quantitative, numbers. A variable whose values are countable is called a quantitative discrete variable. In other words, a quantitative discrete variable only has certain values. There are no fractions in this one, no decimals, no fractions. It's going to be whole numbers, and you might want to write that down. Discrete variables are always whole numbers. Now, if the variable is a measurement, it's called a quantitative continuous variable. Now, what exactly is a measurement? Well, weight, age, believe it or not, because we're never exactly 45 to 25 years old. We're 25 years and 3 months and 2 days and so many hours. It never really completely breaks down to a whole number. So age can be a quantitative continuous variable. Weight, gallons of gas. How many gallons of gas did you put in your car? Have you ever tried to put just 1 or 2 gallons in? You never do that. You're going to have a continuous variable. You're going to have fractions. You're going to have decimals in continuous variables. Now let's talk about the qualitative or the categorical variables. Think about these as I made a box and I put the name of it, the category on the outside of the box, and I'm throwing my surveys into this category. I may be counting them because statistics is nothing without numbers, right? But I'm still throwing them into the different categories that they came out of, that I designed. A variable that can't assume a numerical value is the result of categorizing or describing attributes of a population. It's called qualitative or categorical. Now think about this. Hair color. If I was to say, I split up, I had a box and I had for each hair color, and I counted the number of people in my class that were blonde, brunettes, redheads, that would be categorical variables. What about blood type? What about the type of car a person drives, or the street a person lives on? These are really examples of categorical or qualitative data. Now think about also the attributes whose value is indicated by a label, but that label could be a number, like how many A's in the class, how many children in the family. So I have a category that is 0 children, 1 child, 2, 3, 4, 5, and I can go up until I run out of my highest number is reached that my class submitted, and I could ask each person in the class, how many children are in your family? And I would count the number. I would throw you into a category that just so happened to be a number. 0, 1, 2, 3, 4, 5. Does that mean it's a numerical variable? No, because it's still like a label on a box. I put the label on a box and I threw the people that had 1 child in their family into that box. So that's how we think about it, and remember the difference between the categorical variables and the quantitative variables. Now I've given you a chart to fill in. I just want you to pick a couple of these. This sort of organizes it for you, and you've got it in your guided notes page. The types of variables. Basically, quantitative and qualitative are our 2 main categories, and quantitative breaks down into discrete and continuous. I've given you some examples. Just jot a couple of them down. Under discrete, you could write number of phones, number of children, number of houses. Whole numbers is what we're going to have. Exactly whole numbers, no fractions. Under continuous, you might write length, weight, time, and money. We usually consider money to be continuous because it does have decimals in it. Time. And under qualitative, you might write, gender, age, our group in college, our year in college, something like that. Just pick a couple of those and jot them down on the page that are going to help you remember. Feel free to pick any of your own that you might come up with that are different from these. And now let's do the activity at the bottom of that page. Let's say whether this is a qualitative or a quantitative data set, a piece of data or data set, and then say if it's quantitative, you want to say if it's discrete or continuous. Now I'm going to do a couple of them with you. I'm going to look at the first 2. A, the number of pairs of shoes you own. Well, think about it. Anybody own 3.5 pair of shoes? Probably not. We know it's a number, it's quantitative, and it's a counting number. We're going to count them in whole numbers, so it's going to be quantitative discrete. Now, what about the type of car you drive? If we asked everybody in our class the type of car they drove, and we came up with boxes, and we labeled those boxes with the different car types, and then we threw their name into the box, we are creating groups or categories, aren't we? So this is qualitative or categorical data. Go ahead and stop the tape and finish the rest of them and then restart it, and I'll give you the answers. Okay, C, the distance from your home to the nearest grocery store. Well, distance is a measurement, and a measurement is, of course, quantitative, but now you've got to think, is it discrete or continuous? Since distance has fractions involved, decimals involved in it, we would say it's quantitative continuous. D, the number of classes you take per school year. Well, of course, the number of classes you take is quantitative. It's a number, but anybody take 5.5 classes? It's very difficult to take half a class. So these are going to be quantitative discrete variables. E, the type of calculator you use. Well, a type of calculator, we're going to count the number of calculators of the different types, but the type of calculator itself would be a category. So that's going to be a qualitative variable or categorical. F, the weights of sumo wrestlers. Well, weight is a number. It's going to be quantitative. And there are fractions involved in weight. It's a measurement. Measurements are continuous. So it's quantitative continuous. G, the number of correct answers on a quiz. Well, the number of correct answers on a quiz is going to be counted. Now, most of the time, we would consider that you would get it either all right or all wrong. So we're going to say that this one is a counting number, and it would not have fractions involved. So this is going to be quantitative discrete. H, IQ scores. Now, this one might cause some discussion. Basically, IQ scores would be quantitative, but a lot of times they look like whole numbers. However, I would categorize this as continuous because there could be, it's a measurement of intelligence, an intelligence measure. There could be some fractions involved. Let's go on and finish some more definitions. Let's talk about random sample versus a non-random sample. It's incredibly important how we take a sample of our population because we want to get something, a sample that represents the entire population. We can't be too selective in our sample. We have to be very specific in what we do with our sampling so that everybody has a chance to be represented. Now, definition of a random sample is one that's drawn in such a way that each member of the population initially has an equal chance of being selected. There's several different methods of random sampling. In each form of random sampling, each member of the population has that equal chance of being selected. Different methods have different pros and cons though. The easiest one I can describe to you is called simple random sample, and that just means that in any group of individuals, we have an equal chance of selection, and we'll sort of look at that when we talk about the simple random sample. That's what we're going to think about when we say random sampling in this class. Now, the next type of definition we need is something called a census, and it's a survey that includes every member of the population. Now, it's very difficult to get census data. Look at the United States. We do a census every 10 years, and it's almost impossible to get everybody in the United States to participate. But what we're looking for is pure population data, and that's called census data. Now, a sample, like I said, that represents the characteristics of the population as closely as possible is that representative sample. If I want to look at the scores of my classes when they do a certain instructional technique that I've designed, it's not okay for me to just pick my daytime classes. My day and night students might perform entirely differently on this different instruction that I have given. So I'm going to have to pick a sample that's representative of all of my students if it's going to be a representative sample. There's one more thing I want you to think about when you're thinking about sampling techniques, and that is with replacement and without replacement. True random sampling is done with replacement. That means that once we pick somebody out of it, that member goes back into the population, and then they could be chosen more than once. But for practical reasons, in most populations, simple random sampling is done without replacement. In other words, when we choose somebody out of the population, we don't put them back and allow them to be chosen twice. So most samples are taken from large populations, and the sample tends to be small in comparison to the population. Well, since that's the case, sampling without replacement is approximately the same as sampling with replacement, because the chance of picking that same individual more than once is extremely low, even with replacement. So with replacement, your definition is that each time we select from it, we put it back into the population and then we select another. But without replacement means we select and then we leave it on the side. We take it out completely and don't have a chance of using it again. Now let's take a look at experimental design. We have an experiment that says, does aspirin, we want to look and see, does aspirin really reduce the risk of heart attacks? We want to know, maybe we have fertilizer that we're trying to sell, but we need to prove first that it's better at growing roses than any other fertilizer. We need to know how fatigue works with drivers. Is it as dangerous as perhaps something like alcohol? These are questions that we're going to answer or try to answer using the randomized experiments that we've been talking about. So we have some more words I want you to get used to. When we take as a researcher, when we take one of the variables and we want to see how we can manipulate that to influence the other variables, we call this a designed experiment. Think about your fertilizer. If I want to see how the fertilizer is affecting plant growth, well, I get a group of plants and I use my new fertilizer on it, and I have another group of plants that I don't use the new fertilizer on, and in a couple of months I compare their rate of growth. I have designed an experimental study to manipulate one of the variables, and the variable I'm manipulating is the growth, and the way I'm doing it is I'm using the fertilizer to see if I can manipulate that variable. Now, the next type is an observational study. Now, a researcher in an observational study is not allowed to do manipulation. He merely observes what's happening, or what has happened maybe in the past, and tries to draw conclusions based on those observations. If you look at these two studies and you want to know which one is the strongest one as far as research goes, the designed experiment is by far the stronger. However, observational studies are very necessary. There are certain things that we cannot manipulate. If you're looking at teaching, for example, and you're teaching elementary school children, and you want to say, okay, does this reading study work better? Does it help them to learn to read better than this other one? Well, you're not going to be able to take half of one class and give them the new improved study and not give those other children the new improvements. You're going to have to compare it based on what you see happening. You know what's happened in the past with the old study that you've done, or the old material. You try the new material and you observe what happens. That's an observational study. It's a very necessary part of statistics. So what happens in an experimental study? Well, you have a treatment, or you have something that you do, and we have the group, like I said, that we're going to maybe do fertilizer to, and that group is going to be our experimental group. Well, maybe we give them, a certain solution that's 10%. One group will have another experimental group that we give them 20%, and then another group that will give them 30% of our solution. Those are our three treatment groups. What do we compare them to? Well, we have to have a group that doesn't get any treatment at all. That's going to be called our control group. So let's look at this one. I think I'm on page 6 of your guided notes, but you should be following along with me so you can see this on your page. We are researchers, and we want to investigate whether taking a new medication for a certain chronic disease is going to reduce the risk of death. Now, we got 400 men that we're studying, and they're they're in a certain age category, and they have this disease, and they've been recruited as participants. Now, these men were invited to participate in the study, and they were told they could try the new medication for 3 years. Do you want to participate in our new study with this new medication to see if it will help this chronic disease? Now, think about it. Is this a designed experiment, or is it an observational study? Well, basically, you should say this is an observational study, because these patients were not randomly selected. They volunteered to join a treatment group. Now, in this case, in cases like this, there are lots of reasons a person might join a treatment group. If you are sick with a certain chronic disease and you're not quite so bad off, you might say, experimental medicine, nah, no thanks, I'm not going to take that. But if you're chronically ill and you don't have any other choices, if you're very, very, very sick, this might be a hope for you, your last hope. So it's possible that the persons who decided to take the medicine are in the advanced stages of the disease. So the consequences are they don't have anything to lose by being in the treatment group. They differ greatly from the people who did not choose to take the disease, who were not in the last stages, don't they? So do you think there are going to be different results for the whole population if we only look at the very, very sick patients? This has to be an observational study. It is not a true experimental design. Now let's do this again. This time, we're going to suppose that out of the 400 men who have the disease, 200 are selected at random. Now these people, these 200 make up one group, and the rest of them, the other 200, belong in the second group. One of those is the treatment group. The one is the control group. One will get the new treatment, the new medicine. The other will get a placebo, or something that really doesn't do anything. And then at the end of the study, they'll compare and see how their health is, or how this one was comparing death, so how many have lived through to the end of this treatment. Now is this called a designed experiment, or would it be an observational study? You would be right if you said it was a designed experiment. The patients are assigned to one of two groups, the treatment or the control group, and they were randomly selected for it. That is a perfect experimental design. Now I want to go over with you some math that you do need in this this class, and I know I've hit you with a lot of vocabulary, so let's actually get into some mathematics here for a minute. Let's talk about a data set that we have. It's 5 pieces of data, 5 items in the data set, and it has the numbers of their ages, 23, 26, 26, 39, and 42. We have this variable that we call age, and we say each individual element would be x of I, or x of 1 would be 23, x of 2 would be 26, and you can see I've assigned each of those to the individual data item. And then we have what we call the sum. Now that sigma, that funny looking E thing, says sum everything that comes after it. In other words, add up everything that comes after it. So when we say sum of x, we're saying, when we say sigma x, we're saying sum of x, which is add all of those x's together. Adding all of the variables together means just sum them, and we have the number 156. Now, I want to look back at the same data set and keep going. We have certain things that confuse people, and that's where parentheses are used and where exponents are used. First of all, a, the sum of x, all we have to do is add all of our ages together. We've already done that, haven't we? So you know what a is. The sum of all of those x values would give me the sum of x. But what if I say then the sum of x in parentheses, and then I say squared? In other words, the exponent is outside of the parentheses. What is it telling me to do? Well, it's telling me to first sum all of the values for x. In other words, add them together first, and then square that number. This is quite different from part C. Look at the two. Sum of x squared. What happens first? Now think about order of operations. Which comes first in order of operations, exponents or addition? Well, exponents come first. So what do you have to do first? We have to take each of the data items, each value, and you have to square it. After you've squared each value for x, all 5 of them, we would say 23 squared, 26 squared, 26 squared, 39 squared, 42 squared. Then we get to add them together. Pay attention to B and C, because this is going to be very important as we get over into our formulas. Hopefully you've had a chance to look at this, and if you don't, stop your tape and go ahead and complete this on your paper before you go on and check your answers on the next page. This is the answers that I have gotten. When I summed x, I came up with, adding all the data values together, I came up with 156. When I take 156 and square it, that's the sum of x inside parentheses squared, I get 24,336. And next, if I want to say the sum of x squared, I have to square each value for x first, add those together, and I come up with 5,166. As I said, this is not a random exercise that we're doing. This is something that you are going to have to do in your formulas. So you want to be sure that you are able to understand the differences in these two notations, or these two summations. Now I have an activity for you. It's the summation notation activity, and it has at the top of the page, it has a little chart or a little graph there. It says the values of M and values of X. We sort of think of these as midpoint and frequency. So if I have the midpoints, they're 4, 15, 0, 9, 12, and 8. They align, or they match up with the frequencies of 3, 5, 14, 7, 12, and 6. And my data has been given to me. I've been asked to compute the sum of the M, the sum of all the midpoints, the sum of the frequencies, the sum of the frequencies squared, the sum of the midpoints times the frequencies, the sum of the midpoints squared times frequency, and then the sum of the midpoints, and I want to square that value. All right, so this is not a real difficult task, but usually, instead of looking at it horizontally, I've given you a page or a chart there at the bottom to fill in vertically. In other words, under M, I want you to write the values 4, 15, 0, 9, 12, and 8. Write them vertically. And then match those up with the F values, 3, 5, 14, 7, 12, and 6. Go ahead and fill those in. Now at the bottom, when you finish that, you're going to sum all of the values for M. In other words, you're just going to add them up. You're also going to sum all the values for F. Add those up and write that in. And then you're going to finish the rest of this chart. You're going to come up with the sum of F squared by first squaring every value for F and then adding them. you're going to come up with the sum of midpoint of MF by multiplying M times F and then adding them. And you're going to come up with the sum of M squared F by first squaring every value for M, multiplying it times F, and then you will add them. The chart is the way to go. Now this chart, basically the one I'm giving you on the slide at the top of your page, is the way you'll basically be given the data. What you'll want to do is create the vertical version so that you can do the calculations and then add them at the very bottom. Take a minute to finish filling that in before you continue this slideshow, this video. Check your numbers with me. I've written midpoints and frequencies down. I got those from my data set. I summed them at the bottom, and then I took and multiplied, I squared the frequencies, and then I added the squared versions down there. I said midpoint times frequency, added those together, and then I said square the midpoint, multiply it times the frequency, and add those products down. These should be the numbers that you have gotten out of your slides. Okay, let's do some more definitions. Data that's recorded in the sequence has been collected before we process, before we rank it, before we do anything. And ranking basically is putting it in ascending order. This is called raw data. If I were to ask for the number of smartphones, that should have a T in that smartphones word, the smartphones owned per family, I would get a data set that looks something like this. Maybe this is data from our class, and I say, how many smartphones do you have in your family? And you just gave me back a number. As it is, it's not very useful to us, and raw data isn't very useful. Here's some more examples of raw data. There's a table of 30 students. We call this qualitative raw data, right? Because this is numerical. And it's really maybe it's the age of 30 of our students. And then below, I have the status of 30 students, which is grouping them into what year they are in college, junior, a freshman, sophomore, junior, senior in college. And that's qualitative. I mean, that's going to be more quantitative raw data, isn't it? Because it's going to tell me, it's going to put them into different groups. So if I want to organize and graph qualitative data, what I'm going to look at here is going to be frequency distribution. I'm going to be talking about those. I'm going to be talking about relative frequency and percentage distributions. And then I'm going to be looking at a graphical presentation of qualitative data. So we're really just dealing with some qualitative data here, okay? First, let's take a look at definitions that deal with that. When I set a frequency distribution of qualitative data, what that gives us is all of the categories, think about the categories as boxes with labels on them, all the categories and the number of items, the number of elements that actually fit into each category. Then we create something called a frequency distribution table. Sometimes we just call it a frequency table. This tells us how the frequencies are distributed over the different categories. In other words, if I have a table that represents the hours per week that are worked by students, and I have one group or one category that's 2 hours, one that's 3, 4, 5, 6, and 7. Then I would count the students that work 2 hours per week. Well, there were 3 of them. The students that work 3 hours per week, well, there were 5 of those. There were 3 students who worked 4 hours per week, 6 who worked 5 hours, 2 who worked 6, and 1 student worked 7 hours per week. So that is our frequency table. Really, it's just lining up the category, which is hours per week, and counting the elements or the data items that fell into that category. Let's take some basic raw data here. Let's say I have a class of 30 statistics students, and I asked them what type of donut was their favorite. Now I only gave them 5 to choose from because my favorite is not listed up here, and yours may not be either, but out of these 5 categories that I've given them, they had to choose one, okay? I was very generous because I knew that some of them wouldn't like glazed or frosted or filled or plain, so I gave them the category other so they could fit into that other category. Now I want to create a frequency distribution table or a frequency table for this data. How do I do that? Well, I've given you an example here on your guided note page of a frequency table. First, you're going to write down the donut category. So the first thing you're probably going to write down is what fits into the category. Well, let's say glazed you write down first. I don't know what you're going to write down first, or frosted would be next, filled would be next, then I've got plain, and then I've got other. And then you're going to go count the number that are in each category. Now you can use tally marks to do that. That's why I'm giving you a column for tally. And you can say, okay, well, glazed, and then just kind of check it off. And you can do that at the top of the page. You can mark through it as you tally it up. And then count the tallies. You'll have the frequencies. When you sum all of your frequencies, hopefully you come up with the number 30. So complete your frequency chart right now. Okay, hopefully your chart looks a little like this. Now, you might not have written them in the same order that I have them here, plain, frosted, filled, glazed, and other, but your tally should be representative of these different categories. You should have 3 that are plain, 5 frosted, 7 filled, 8 glazed, and 7 other. When you sum those up, the sum is 30, and this is a frequency table. Note that that tally column is not usually included in the frequency table. That's just a working column that I gave you to get started creating your very first frequency table. But it's not usually included. All we have is the category name, which in this case is variety of donut, and we have the frequency column to create our frequency table. Now let's talk about how we take it a step further. We want to create a relative frequency table and a percentage table. And what we do after this is you first have to create the frequency table, and then you'll create what's called a relative frequency table by taking each category. You'll take the frequency and then divide it by the sum of all frequencies. Now the sum of all frequencies in our donut data is 30. Because we had 30 donuts total. So the sum of all frequencies is the sum of our sample size or our population size, whatever we're using. The frequency divided by the sum of all frequencies gives us a relative frequency. It tells us how that category relates to the rest of the data items. Now, once you have a relative frequency, which is a decimal, you can take it and multiply it by 100% to get a percentage. In other words, relative frequency times 100% is the percentage, and this would create, from the relative frequency table, it would give you a percentage distribution table. You have a chance to do this. At the bottom of the page that we're working on in guided notes, go ahead and create the relative frequency. In other words, for the plain category, you're going to say 3 divided by 30, and you're going to come up with that frequency. Well, 3 divided by 30 is going to give us 0.1, and 0.1 is the frequency or the relative frequency for the plain category. How do we get it to a percentage? We'll multiply it times 100 and add a percent sign. So when I say 0.1 times 100, I get 10%. Don't forget to write your percent sign in there. It's important for you, okay? You'll sum those at the bottom. You'll have the sum of the relative frequency, which should equal 1, and you'll have the sum of the percentages, which should equal 100%. So here's the completed table. And you can see after I add all of my decimals in the relative frequency column, they equal 1. In other words, they equal the whole. All of the relative frequencies added together should always equal 1 or very, very close to 1. Sometimes because of decimals and rounding, it might be 0.99 or it might be 1.001 or something like that. Now percentages, they should have percent signs out here beside them. But you're going to say 0.1 times, and you just have to multiply the relative frequency times 100%, and that gives you the percentages that fit in your percentage distribution. Now let's go on and talk about the quantitative data, frequency distribution with quantitative data, and constructing frequency distribution tables and relative and percentage distributions, and graphing grouped data. That's what we're going to go to next, except for instead of being qualitative, this time it's going to be with quantitative data. So what we have to do when we have quantitative data is we have to create a class. think about what quantitative data involves. Well, quantitative data can be numbers, it can be quantitative continuous, so it can be a range of numbers. And so we're going to have to create a class that has an interval in it, and that interval, in other words, the beginning and the ending point, will include all of the values in the data set that fall within two numbers. We call those numbers the lower and the upper limits of the class. So the lower limit of a class, that's the smallest data value that can actually go in that class. The upper limit of a class, well, that would be the largest data value that can go into that class. Class boundaries are something a little bit different. They're the halfway points that separate the classes. In other words, a lower class boundary of a certain class, we get it by averaging the upper limit of the previous class and the lower limit of the given class. In other words, we go halfway between the two classes. Upper class boundary, we're going to go halfway between the class that we're in and the lower limit of the next class. And you'll see this in an illustration in just a minute. A frequency distribution for quantitative data basically lists all the classes and the number of values that belong to each class. So it's sort of the same thing, except for instead of dealing with, plain donuts or filled donuts, we're dealing with a class, the numbers 0 to 5, the numbers 5 to 10. Our class has groups. We grouped the data, and that's why it's also called grouped data. We call these frequency distributions that we're dealing with, we call them quantitative data, which is grouped data. Now I'm giving you an illustration here, and I want you to fill in some of these blanks on your page and looking at the different classes. If I have individuals that attended the new Disney movie, and the class I was looking at was what ages were the people that attended this movie, and I created my classes. I said age 11 to 20, and then I went 21 to 30, 31 to 40, 41 to 50, and so on. And, I created those age groups myself, and then I counted the number of individuals that were in the age group, and I said, okay, well, there are 18 that were between the ages of 11 and 20, okay? So where are these, and what exactly are we talking about here? This is the variable, is age group, and you can see the classes. Well, the 11 to 20 is the first class, 21 to 30 is the second class, 31 to 40 is the third class, so 41 to 50 would be the fourth class. The first column there is going to be the lower limits of the classes, 11, 21, 31, 41, 51, and 61. And the upper limits of each class would be the top number, the highest value that can be in that class, well, 20, 30, 40, 50. Now, what's not on here is the boundaries, right? The boundary would be the halfway point between each class. So between class 1, which is 11 to 20, and class 2, which is 21 to 30, we would say, what's halfway between those two? Well, 20.5. That's the boundary, isn't it, between the two classes? So that's what we're talking about when we say boundary. It's sort of the cutoff thing. Now, the number of individuals that are in the classes, well, that's the frequency. Those are the frequencies that we counted. So then we call that the frequency column. And this is what a frequency distribution looks like for quantitative data. It has to be grouped because there's no way that I could just look at, well, how many 11-year-olds or there are too many variables. It just wouldn't make any sense. It would be like having individual items, too many individual items, and not enough in a certain category. So we group them together to help us make sense of them. So how do you calculate something we call the width of a class? Well, the width of a class is really the lower limit of the next class, the bigger class, minus the lower limit of the current class. We take that, it's always the widths of classes. When you set your classes up, you're always going to set them so that they're the same width, but otherwise the data would not be equally represented. It doesn't make sense. So we need the same width of classes. So if I take two of the classes, any two classes, and I say, okay, class 1 and 2 down there, and I'm looking at the lower limits, well, that's 11 and 21. I'll take 21 and subtract 11. I'm going to always go the bigger one minus the smaller one. 21 minus 11, and I get 10, don't I? So what is the width of that class? Well, it's 10. Now check them. They should all be 10. When I do the next class, it's going to be 10. It's going to be 31 minus 21. The third one is going to be 41 minus 31. And we're always going to have 10. And we will assume on that last class that we would have 71 would be our next lower limit, even though it's not listed. So we can say 71 minus 61 for the last one. In other words, all of the class widths should be the same. Once you find one, you should have found them all. What are the boundaries of the class? Well, remember, we go halfway. Well, halfway is going to be 0.5. So I'm going to go for my first class. I'm going to say it goes, the limits are 11 to 20. So the boundaries would be 10.5 to 20.5. And those are the boundaries. They're halfway between the classes. Now, another definition you need is the midpoint. The midpoint says take the lower limit of the class, add the upper limit of the class, and divide it by 2. In other words, what's halfway in that class? Split that class right down the middle. What's the halfway point? So in the first class, I would say 11 plus 20. Well, that's going to be 31. When I say 31 divided by 2, I get 15.5. Most of the time, your midpoints are going to have decimals of 0.5. And these all do. So we got 15.5, 25.5, 35.5. Take a second, make sure you understand how we're getting these calculations before you move on. Now, I want to take some rather complicated data, and I want to create one of these tables with you, which means we're going to have to come up with our own groups for the data. And really, this is Major League Baseball value of Major League Baseball teams in April 2021. And I came up with this trying to kind of get us something that we could relate to a little bit. Now, these are already ranked in order. That kind of helps us. The New York Yankees is the most valuable team at $5,250 million. And the Miami Marlins are the least valued team at $990 million. So we're going to kind of look down at this and say, okay, how do I continue? How do I fix these together and create my classes of data? Well, I have to make some decisions. First, step one, and I put this on your page there for you to think about. You have to approximate the width of the classes. Now, I've decided, I made a management decision. I'm going to group this data into 6 classes, equal width. All classes have to have equal width. So I have to figure out, what is that width going to be? And then I need it to be rounded to a number that's convenient for me. It needs to be not a decimal. So I'm going to come up with a lower limit then, and then I'm going to set the class limits for each class. And then after I have the limits, I can tally the data in the classes. I can calculate the frequency and the sum of the frequencies, and then I can calculate the relative frequency, and then I can calculate the percentage of each class. It will take it from raw data, which is what you're looking at right now, all the way through a percentage distribution table. So let me show you what I've got here for this one, and you can fill in your chart as we go along, okay? First, I said the minimum value, the smallest, the least valuable team there listed was 990, and the maximum was 5250. So I'm going to group it using 6 classes. I would say, what range do I have? Well, 5250 minus 990, I would divide it into 6 classes, comes up with about 710 per class. Okay, it's not a real convenient number, but I'm going to go up. I can't go down, but I can go up, and I'm going to create my width of the class at 750. I'm going to say I have 6 classes, 750 is the width. How do I get the lower limit of the first class? Well, it needs to be below 990, doesn't it? It could be 990, but it kind of needs to be below 990. So I'm going to go to something that's convenient for me. Since I know I'm doing this in 50s, ending in 750 is the width, I'm going to start with 951. That's below 990. It's pretty close. I just picked it, and it sort of fits with my pattern. So I'm going to say 951, and I have a width of 750. That gives me my next lower limit would be 1701. Now, the easiest way to do it is create your lower limits and then create your upper limits. So I said 950 plus 750 gives me 1701. 1701 plus 750 would give me the 2451. And keep on, go on until you get all 6 classes down there. Now I've given you the widths, and the width, notice that when I go up to 1700 as the upper limit for the first class, and then 1701 is the lower limit of the next class, they all follow a consistent pattern so that they are 750 wide. Next, do the tallies, right? what teams fell into each of those categories. So then you get to go back to your raw data and count. You're going to say, how many teams fell into the category of 951 to 1700? Well, that's pretty easy. You can go and count them. The Marlins, right? The Tampa Bay Rays, and go all the way from 990 all the way up to 1700 and put them in that category. And then you got the 1701 to 2450, 2451 to 3200, and so on. So you calculate you do your tallies, you add them up, and you get the frequencies and add the sum of the frequencies at the bottom. Relative frequency, well, you take that frequency and divide it by the total number of teams. We should have 30 teams listed, right? So it's going to be divided by 30. And then, of course, for percentage, all you're going to do is multiply times 100. And make sure that you try to do this on your own before you go to the next slide. But I'm going to go on here and show you the filled-in chart. I found there were 17 teams in that lowest category. There's a relative frequency of 0.57. That means 57% of my teams fell into that lowest category. Let's look at my next categories. There were only 27% that fell into the second category, and even less, 3% in the third. 10% go into the fourth category. Nobody was in the fifth category. Why did I have it? Why not just delete it? Because look how important it is. It tells me that there's an entire category between that highest valued team, which is the New York Yankees, and any other baseball team. It tells me that there's a blank category. In other words, that team is extremely valuable compared to the rest of the baseball teams. When I add up my relative frequencies, I have a sum of 1. When I add up my percentages, I have a sum of 100%. And I've checked, I added up my frequencies, sum is 30, and that's the number of teams in my data set. Incredibly important that I do these sums to check my data. Now, on the next page, which I don't have on your slide, so I'm going to tell you what to do, and then you can see Blackboard for a solution to this later on. There's an activity. It's an on-your-own activity, and these are ones that we don't do in class, but you should be able to fill them in. It's research with cell phones owned by 24 families. Now, I want a frequency distribution of this data, and these are single-valued classes. Underline those words. In other words, you're not going to have a lower limit and upper limit. The value is going to be either 0, 1, 2, 3, and it's going to go all the way up to 9. So you can go ahead under cell phones and you can write 0 is the first class, 1 is the second class, 2, 3, 4, all the way up to 9. Then you're going to write tallies. You're going to figure out how many of those go into each cell phone category, into each class. And then you're going to do frequencies. Now, what is the frequency? Well, it's actually the number of cell phones owned by 24 families. So it's the number of families, isn't it, that own the cell phones. And next, the relative frequency, we would take it and take the number and divide it by the total number of families, which we have 24 families, don't we? And then we're going to take for percentage and multiply it by 100. I have a question that I'm asking you at the bottom of the page. What's the relative frequency of families who own fewer than 4 cell phones? Now that's going to include more than one different category. So think about it. How are you going to find the relative frequency of families who own fewer than 4 cell phones? So it's a little complication that I want you to think about. Now we've got one more type of table to learn. This one is called a cumulative frequency distribution. A cumulative frequency distribution gives us the total number of values that fall below the upper boundary of each class in our table. So when we calculate it, we have to add all of the categories that come before the category that we're interested in, add them up, and divide it by the total observations in the data set. So I want to do an example with you so that you can look at this one. And we're going to use our baseball data once again, okay? Now I've given you the numbers you had on the other page. You came up with the different categories that we came up with for the value of the teams and the number of teams that fell into each category. And that's how we're going to get started. Now, we need to come up with what we call, at the bottom of the page, the cumulative frequency. So what that's going to be, the first category I've listed for you, it says 951 to less than 1661. Okay, so how many fall into that first category, right? 951, and it's really just 15. But the next category still starts at 951. It goes from the very beginning, and it includes the first two categories in our chart. So it goes 951 to less than, and it would go 2411, wouldn't it? So we would add everything in the first two categories. I would have 15 plus 9 would be the frequency. Now I've gotten you started. See if you can do the cumulative frequencies. Label your categories, the cumulative categories, get the cumulative frequencies down, and then it's simply a matter to get cumulative relative frequency. You take the cum frequency and you divide it by the sum of all frequencies, so they're always going to divide by 30. And then percentage, we're going to multiply that cum relative frequency by 100. So let's take a look at page 13 in your guided notes. And this is a great example that we can use to see if we can create our own frequency distribution table for grouped data. I've given you a list of baseball teams, and these are all of the baseball teams leagues in the United States, and they are valued in millions of dollars, you can see, starting with the most valuable team, which is the New York Yankees, $5,250 million, down to the least valued team. Least valuable is the Miami Marlins at $990 million. So this group data is already, this data is, as it is, not grouped, but we've got to create some groups because it makes no sense to graph them. Each individual team, as you can see, has a different valuation to it. So we would just have a bunch of bar graphs that were all the same height, and there would just be one team in each one. And that doesn't help us a lot to evaluate how valuable these teams are in relation to each other. So we do something called grouping. And we have to make some decisions as the researcher. And I've written these steps down here below for you. First, you have to find the width of each class, how big you want it to be. And to do that, the first step, of course, is to decide how many groups you want. I've made a decision. I want to do 6 classes of equal width. So I'm going to look at my maximum value team, which is, of course, 5,250. And my minimum value team, which is 990, and I'm going to come up with the width of the classes. I'm going to say this width is going to equal that most valuable team minus the least valuable team, and I've decided I want 6 classes, so I'll divide that by 6. And that'll kind of give me a width. Well, it comes out to be 710. That's not a really great width for my classes, so I can't go down below it. 700 would be perfect, but if I do that, I'll leave out one of the teams at the extremes when I do it, so I have to go above. So I'm going to say this is going to be about, and I'm going to use 750 because 800 just seems too big to me. So I'm going to say my width of my classes is going to be 750. Now I have to make a decision. Where am I going to start? What's my lowest value of class? Where is it going to start? What's the lower limit going to be? And I want to go below the least valuable class, which is 990, and I want to kind of make it fit with this 750. So I'm going to make a decision to start with something like 950, except I want it to be ending in a 1, okay? Just because that's the way I like to see my charts go, and you could have made it 950 and you would have ended on an odd number, but I made the decision as the researcher you would do that, and that's where we're going to begin. Let's go down and create the frequency table from this data. So I've given you a little chart at the bottom to fill in. What you need to do is say my starting first class lower limit is going to be 951. Of course, it's going to end 750. It's going to have 750 spaces in it, or 750 units in it. But the easiest way to do that is to say 951 plus 750 to get the next lower limit. So when I say 951 plus 750, I come up with 1701. And then I add 750 again, and I come up with 2451. I add 750 to the next one, and I have 3201. And then keep on. 750 plus 750 gives me 3951. And plus 750 for the last one is going to give me 4701. Now, they've all ended in 1s, that's right. And they're all going to end just before the lower limit of the next class. So in other words, my first class here, and I'm going to just kind of number them. This is class 1, this is class 2, class 3, class 4, class 5, and class 6. Now my first class here is going to end just before 1701. What is that number going to be? Well, it's going to be 1700. The next one would end just before the third class, 2451, so it's going to go to 2450. And so on. Now you can see what I'm really doing is I'm taking 1700, I'm adding 750. I'm adding 750, I'm adding 750, I'm adding the class width to each one, because there should be 750 between upper limits, just like there are 750 between lower limits. So I'm going to finish this up. And I get down to 4700, and I have to kind of say, okay, the next one is going to be plus 750, isn't it? I would take this upper limit here of 4700, and I would add 750 to it, and I'm going to come up with 5450. Right, I have my classes, they're perfect. Okay, I would check that if I were you, but this is probably right, but check it anyway, make sure. And now we're going to go find the baseball teams, and where do they go? Well, usually our data is not listed for us in ascending order or descending order like this chart is. And I got this off the internet for you, and so it was already listed like that. Usually they're not. If they are, like this is, tallies might not even help you. You can just count the teams. I want to go between 951 and 1700. I could sort of circle them, 951 and 1700. That includes every one of these teams, doesn't it? All of these would be included, plus, let's see, these two, okay? And this would kind of be my cutoff. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 17 teams that are in the first class. Now, let's find the second class. I want to go between 1701 and 2450. Between 1701 and 2450 takes me all the way up to, well, right here. This team is worth 2450. This is going to be the second class. I can put a 1 by this one. So that's going to be the second class. 1, 2, 3, 4, 5, 6, 7, 8 of those. Between 2451 and 3200. Well, that's not many, is it? There it is. There's only one of them. This is the third class. There's only one team in that class. What about between 3201 and 3950? Between 3201 and 3950 takes us all the way up to here. In other words, there are 3 of them in class 4. Now what about the next group? The next class or group is 3951 to 4700. There aren't any teams that fit in that category or that group, so we'll say there are none, just 0. Now, it doesn't mean we get rid of that category, because it's important to see the distance between the New York Yankees and the rest of the baseball teams, their entire category gap between them. And of course, the New York Yankees are the only ones in that highest category that go up to 5450. So what's the relative frequency? Well, we have, up here it tells us, we have 30 baseball teams. That's the sum of all the frequencies right there. So what are we going to do to get relative frequency? We're going to take the frequency, which is 17 here for the first one, and divide it by the sum of all frequencies. So that's going to be divided by 30. What's that going to be? It's going to give us, and we'll just go to 2 decimal places, 0.57 for that one. So how do I get the next one? Same thing, 8 this time, divided by 30. This is relative frequency. Think about it. It's how this group relates to the other groups in the data set, okay? So this one had 8 in it, so 8 divided by 30, well, that gives me a 0.27. And here's just 1 divided by 30. I'm going to get a 0.03 with that one. What about 3 divided by 30? Takes me to a 0.1. 0 divided by 30 is going to give me 0. And here's another 1 divided by 30, which I know already is 0.03. Now I would do the sum of all these, and it would come out to equal the number 1. It should be very close to 1, but this one, add them up, it is exactly 1. And also you probably would sum this column because you want to know how many teams you've got. I already told you there were 30, but let's sum the frequencies anyway. Percentage distribution is pretty easy. All we do is multiply it by 100. Relative frequency times 100, add a percent sign. And then you would sum those for your table, and you would see that they sum to 100%. Now this is a frequency distribution table for grouped data, which is really handy since most of your data that's numeric is going to be like this. It's going to be something that doesn't make any sense to not group it. If it's not a discrete value, if it's continuous, then and money is, then you're going to want to group the data. Now I have an activity for you that's on page 14 of your guided notes that I just want to kind of get you started on because it has a special condition. It says do a frequency distribution table using single valued classes, single valued groups, if you will, okay? So what is it that we're talking about? Well, this is the number of cell phones that are owned by 24 families. Let's say we surveyed the families or the students in our class and we said, how many cell phones does your family own? And these are the numbers that we were given. So we can see the lowest number I see is somebody's family doesn't have any cell phones. And then they go all the way up to 9. So 9 is our highest valued, our highest group. Now, do we want to put these in? We don't. We're choosing single valued groups, like each individual number is its own group. In other words, here's my groups, okay? I'm going to just put groups are over here. And the groups are cell phones. There's 0, and I'm going to go all the way up to the number 1. Why? Because even if nobody falls into one of these categories, just like with the baseball teams, I don't want to leave a gap. Now, I'm going to go through and count them and see how many, and that's what the tally column's for, so you can see how many families fell into the owning 0 cell phones, how many families fell into the owning 2 cell phones. That's what you're counting. That's the frequency. What are you counting? Well, you're not counting the number of cell phones because this is the number of cell phones. What you're counting is the number of families. The number of families that owned that many cell phones. So keep track of what you're doing. And then you can create your relative frequency. Don't forget, sum these at the bottom. They're not going to come out to exactly 100%, but it's going to be okay if it's a little bit off, and you'll see how that works. And then go down here and answer one last question when you finish. What's the relative frequency of families who own fewer than 4 cell phones? So you're going to have to go to less than 4, which will be these groups, right? And you're going to have to count that frequency and divide it by the sum of all frequencies again. How many families do we have total? And you'll get the frequency that own fewer than 4 cell phones. This will help you to understand, if you really do understand, creating a frequency distribution table for grouped data. And I will post this answer sheet for you after a while. I'm going to stay with your guided note pages for just a little bit here for the last couple of pages because we have some things that are kind of confusing and I want to walk you through them. This is a cumulative frequency distribution table that we're going to talk about now. And a cumulative frequency, and I'll let you write that down in the blank. A cumulative frequency distribution, it gives us the total number of values that fall below the upper boundary of each class, okay? Of each class. So I'm going back to my baseball teams, and I've already just kind of taken and recreated that frequency distribution table for you. The first group, of course, had 17 teams, and the second group had 8, and you remember the data. So we can work with it. I just wanted to recreate it on this page for you. Let's talk about cumulative frequency and cumulative relative frequency. Now, cumulative frequency of the second group, and remember, this is group 1, this is 2, this is 3, 4, 5, and 6, okay? So when we say the cumulative frequency of group 1, well, it's everything that falls below the upper boundary of that group? Well, that would be only 17. I mean, the cumulative frequency of the first class is the first class, right? What about the cumulative frequency of the last class? Well, it's the number that's in that last group and everything that falls below it, everything in a lower group. Well, that's everything. So the cumulative frequency of the last class is always the sum of all the frequencies. It's always going to be everything. So you know the first class cum frequency and you know the last class cum frequency. What about those in between? Let's kind of look at number 3, group 3. Well, it includes the frequency of group 3 and any class below it. That would be group 2 and group 1, okay? So any smaller class, and remember, they're written like this, so any smaller class comes above it. It would be, what's the cum frequency of group 3? Well, it'd be 1 plus 8 plus 17. Cum frequency of group 4, 3 plus 1 plus 8 plus 17. And that's really all it is. Now, how do you get the cumulative relative frequency? That relative frequency always means you're going to divide by the total observations in a data set. So you're going to take the cumulative frequency that we just figured out and you'll divide it by the sum of all frequencies and you'll have a relative number. To get a percentage from that, multiply it by 100%, okay? And that would be your cumulative relative frequency. So let's do this real quick. Taking our baseball data, the value of the teams, the cum frequency for group 1 is going to be anything that is 951 to below, and I just listed it like that. It really go through 1700, but it's really anything that's below the next group, isn't it? That's what falls into group 1. So I said anything less than 1701. Well, the cumulative frequency of that would be just the first group. Relative frequency, well, we already said that, 17 divided by 30, and that came to 0.57. Cum percentage or cumulative percentage is going to be, we'll multiply the relative frequency times 100%. That's easy. Let's look at number 2. This time, it's going to include group 1 and group 2. So it's everything below that third group, that 2451, okay? So it's anything in group 1 and 2. So it's really 17 plus 8, and that's going to be 25. How do I get the relative frequency? Well, this will be 25 divided by 30. That'll give me 0.83 or 83%. Next group. The third group, well, it has to be anything that's in group 1, 2, or 3. So it's going to be everything that falls below the next highest, that group 4, which is going to be below 3201. So I have the 17 in group 1, the 8 in group 2, and how many in group 3? The 1 in group 3. Well, that's going to be just 26. When I divide 26 by 30, I get 0.87 or 87%. And let's see if you can do group 4, group 5 on your own, and group 6. Okay, stop the video. Start back when you're finished. Okay, hopefully you had a chance to complete this chart. So let's say the fourth group, everything is going to be below that fifth group. Well, that fifth group was 3951, wasn't it? It's the first group of 17, second group of 8, third group of 1, and what's in the fourth group? Well, there are 3 of them. That's going to be 29. 29 divided by 30 is equal to 0.97. Almost all of the baseball teams, right? What happens to the fourth group? Well, it's everything below, the fifth group. It's everything below that 4701 that starts my sixth group. So I really had 17 plus 8 plus 1 plus 3, but there's nothing in the fifth group. So it's going to be exactly the same as the cum frequency of the previous group, isn't it? Another 0.97. And the last one, like I told you, it's going to be everything that's below the next number up, which would have been 5451 if we had continued and had a seventh group. So I'm going to say it's 17 plus 8 plus 1 plus 3 plus 0 plus 1. But like I told you before, the last group, cum frequency, is always going to be everything. So it's going to be 1 or 100%, because it's take every group, that group, and everything below it. Well, that's everything. Page 16, let's take a look at some more summation notation. In other words, let's take a look at some more algebra concepts that you're going to need for the formulas that we're going to take over very soon. This one says that there's a table, has information on NCAA men's basketball championship tournament final 4 teams, and there was a 33-year period, and the table shows how many teams with each seeding qualified for the final 4. For example, 54 of the 134 final 4 teams were seeded 1, 28 were seeded 2, and so on. So they've given you some directions here. Y is going to be the seed, and I would say Y is this row right here, and X is the number of teams that have that seed, so that's my X. Now normally I would take this, and you might want to do this because this is on your own activity, I would take it and I would write it vertically. I'd write 1, 2, 3, 4, 5, and then I'd go beside it because it makes it easier to do these calculations. But if you're going to just do it this way, you can say the sum of X, well, add all the X's. The sum of Y, add all the Y's. The sum of X times Y, well, you might want to come up here and say, okay, here is my X times Y, and I take these numbers and I say 54 times 1, 28 times 2, and I go on and do that, and then I add them together. So work and see if you know how to do these summations. And remember, for this one, for D, this is the tricky one, you have to square every value of Y first before you add them. So you might want to come up with a column maybe that says Y squared, or row, and then square all the values of Y before you add it. Now I've done the same sort of thing down here with pizza deliveries, except the list is up here in the narration, so you're going to want to create a table that has X in it, and you're going to list those values for X, 48, 103. These are pizzas delivered. These are my variables I'm talking about, so these are my X values. 136, and then you're going to want to see what you do with those. You might want to come up with a column that says X squared so that you can sum all those X's that are squared, and then you're going to want to sum the value. The sum of X has to be squared. You've got to know the difference of these before you hit the next formula section. Again, this is an on your own activity, and I will wait until you are finished with it and post your answers when somebody asks me about it. But this is the conclusion of Chapter 1 as far as the lecture section goes. Now, I should have some extra problems worked for you in other lecture videos, and if I put those up, just keep an eye out for them. Otherwise, you should be, after you finish this lecture, you should be able to go and work all of your problems that are in my Open Math Lab.